So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice. Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave.
That whimsical caution hints at a profound truth. Black holes are not destinations for the curious traveler. They are cosmic enigmas that defy our understanding. Yet a revolutionary study, published mere days ago, challenges what we believe lies at their heart. With exclusive footage from NASA illuminating these phenomena, we embark on an exploration that may reshape our view of the universe. This is a journey into uncharted territory. Join us. Today we delve into a paper from Physical Review Letters released on March 11, 2025, which proposes that the singularities within black holes may not exist as we've long assumed. Enhanced by NASA's striking visuals, this investigation bridges theory and observation. Let us begin with the enigma itself. At the core of every black hole lies a singularity, a theoretical point of infinite density and zero volume, where space and time cease to function as we understand them. This concept has perplexed scientists for generations, raising a fundamental question. Can nature truly permit such an anomaly? To frame this, NASA offers a perspective on what black holes represent. Black holes are one of the most searched terms about our universe, a region of space with gravity so strong, not even light escapes. But a lot of what we think we know? Myths. And the greatest may be the singularity itself. This new research suggests an alternative, one that demands our attention. The study introduces unimodular gravity, a variation of Einstein's general relativity, where the universe's total volume remains fixed and time assumes a distinct role. When paired with the quantum principle of unitarity, which insists information cannot be lost, the singularity dissolves, replaced by a region of quantum uncertainty. To connect this theory to reality, NASA's observations provide a vital link. This image, captured by the Event Horizon Telescope, reveals the boundary of a black hole. Yet the new research posits that beyond this horizon lies not a singularity, but a quantum domain, an idea we'll explore further. Stephen Hawking showed black holes aren't totally black. Radiation leaks out as Hawking radiation, causing them to evaporate over time. The Event Horizon Telescope confirmed Einstein's predictions, but there's more to learn. Hawking radiation suggests black holes are not eternal prisons. If they evaporate, what remains? The study proposes a quantum state, not an infinite point, a shift that challenges our deepest assumptions. Envision this quantum region, a domain where the rigid structure of space and time softens into uncertainty. No crushing singularity, no absolute event horizon, just a state of quantum flux. The study's authors argue this may not be limited to theoretical models, but could describe all black holes from stellar remnants to galactic giants. This scene reveals the chaotic dance of matter around a black hole millions of times more massive than our Sun, nestled at the Milky Way's core. While we observe its outer effects, the interior remains hidden. The research posits that within lies not chaos, but a structured quantum state, an idea that reshapes our understanding of these cosmic titans. The paper details how this quantum region emerges from the interplay of gravitational constraints and quantum coherence. Unlike general relativity, which predicts an inevitable collapse, unimodular gravity introduces a cutoff, preventing infinity. This aligns with efforts to reconcile gravity and quantum mechanics, a quest that has eluded physicists for a century. The implications of this discovery extend far beyond black holes. Singularities underpin theories of the universe's birth in the Big Bang and its evolution through galactic formation. Resolving them could illuminate these foundational events, offering a clearer picture of cosmic history. Here, a galaxy glows with a brilliant core, a supermassive black hole at its heart. Evidence suggests these giants co-evolved with their galaxies over billions of years, a symbiotic relationship. If their interiors are quantum rather than singular, our models of cosmic growth must adapt. This breakthrough could even hint at traversable pathways, wormholes bridging distant realms, a notion once confined to speculation. Moreover, the resolution of singularities addresses a paradox in quantum field theory. How can information survive in a universe with such extremes? By replacing infinities with finite, quantum states, this framework offers a pathway to a unified theory of quantum gravity, an elusive goal that could redefine physics itself. The researchers propose that this quantum resolution applies to real black holes, such as Sagittarius A star at our galaxy center. Current observations, while powerful, cannot yet probe this interior. However, advancements in technology, telescopes capturing finer details, or quantum simulations may soon test these claims. These images revealing the turbulent surroundings of a black hole are a testament to our progress. Future missions may discern whether these objects harbor quantum realms rather than singularities. If confirmed, black holes would transform from cosmic endpoints into windows, gateways to new dimensions of understanding. The study's reliance on an anti-de Sitter model, a simplified spacetime, raises questions about its universality. Yet the authors suggest that with further refinement, this approach could extend to the Schwarzschild and Kerr black holes we observe. Such a leap would require reconciling theoretical elegance with the messy reality of astrophysical data, a challenge for the next generation of scientists. Through the lens of unimodular gravity and quantum mechanics, illuminated by NASA's vivid imagery, we stand at a threshold. The singularity, long a symbol of the unknowable, may give way to a frontier of discovery. What lies within these enigmatic objects? A quantum tapestry, perhaps, woven into the fabric of the cosmos. Subscribe for continued journeys into the universe's mysteries. Until next time, this is Misty Q Time, seeking answers beyond the horizon.